Hello guys and welcome to a new video. Today we are talking about a feature which makes Rust unique, which is ownership. Ownership means which variable owns the data within a certain scope. So for example, let's say we have a variable s1 which is a reference to a string. Let's just say to the string hello. So what happens when we do this? So here we are assigning s1 to a new variable called s2. Let's see what happens if we try to print the standard output s2. S1. So the script won't compile because we have an error. It says borrow of moves value s1. So basically the compiler is saying that s1 no longer exists and the data it refers to, which is the string hello, is now referenced by s2. So what can we do instead is to print s2. Let's see now. Okay, this is correct. And so basically guys, this is ownership. And this has to do with the difference between how the data is saved either on the heap or on the stack. So in the stack, the compiler saves data which has a fixed size at compile time, while on the heap you store data which is not known in size at compile time. So Rust will never automatically create deep copies of your data on the heap. What can we do to enforce it is to use the clone method. So we can do something like this. We can use the clone method on s1 and now we can print s1 to the standard output. As you can see here, now it compiles nicely. So in this case, the string hello which is referenced by s1 is stored on the heap because we don't know at compile time what its size will be. While for example, if we deal with integers or float or any fixed size variable, we know what the size will be at compile time, so it's quick to make a copy of them and these values get stored on the stack. So they can be copied into other variables. What I mean by that? So let's say for example we have a variable x which contains 5. So x represents an integer. And let's say we do this assignment. So when we try to print both x and y to the standard output, this time we don't have errors. And this is because the compiler knows that an integer takes a fixed size on the stack, so x will be copied, or rather the number 5 will be copied inside y. While when we are dealing with data which is stored on the heap, we are not talking about copy anymore. So this is a copy. And the variable x here is stored on the stack. while in the case of the strings, this is stored on the heap, and when we do this assignment, so let s2 equals s1, this is not a copy anymore, this is a move. And so basically here s1 goes out of scope, and so is no longer accessible. Okay guys, so this is the difference between data stored on the stack and data stored on the heap. So again, just to fix this concept, data can either be moved or be copied. So let's see another example. Let's define two functions which are called take ownership, and these will accept a string, and another function which is makes copy, and this will accept it will accept an integer. So they will have pretty much the same body, so we are just going to print the argument to the standard output. And the same goes for make copy. But the difference in the behavior is how they take ownership of the data. So if we pass s2 to take ownership, and we make a copy of x, x will still be accessible, but s2 will not, because s2 will go out of scope. So how can we see that? Let's just print to the standard output the variables. So x is still accessible. Okay, let's just compile this. Oh, sorry, this is I. So let's just compile this. Okay, so we can see that S2 is accepted inside take ownership and is printed to the standard output. The same goes for X within make copy, the make copy function. And then after the scope of the make copy function is ended, X is still accessible. So in this case, X has been copied into the function, so as the argument I, as the parameter I. The same doesn't hold for S2. So here S2 will not be accessible and the script won't compile. So is S2 still accessible? And the answer of course is no, and we're gonna have an error. So this parameter takes ownership of the value. So S2 is moved into the parameter S, and one suggestion from the compiler is that we can clone S2 into S. Now we are not gonna do that, but this could be a solution. Although clone of course is not so good for performance because we are gonna duplicate our data on the heap at runtime. So let's see that with another example. So let's just comment this section. So let's define another function which will be compute length. And this will accept still a string. and it will return the length. So this is gonna return a usize. Okay, so of course in practical applications we have functions that consume the data, but we still want to retain our data in the main scope. So in this case within the main function. And if we pass s2 or let's say s1 to the length function, so if we do like this, compute length of s1 now when n is computed, so outside of the function, at the end of the function compute length, s1 will no longer be accessible because it is moved in the parameter s, and this is not practical because we are not gonna we don't want to return also s every time. So we could do just like that. So we could define the return type to be a tuple, usize, and string. But this is not practical. It's not an efficient way. So one nice feature of Rust is reference. The reference is similar to how pointers work in other languages such as C++ and C. So basically, a reference is a variable which holds in itself the address of certain piece of data. So a reference can be thought of a pointer linked to data owned by another variable, but unlike a pointer, a reference is always guaranteed to point to a valid memory location for the life of the reference, while in other languages such as C, the programmer has the responsibility of freeing the memory when it's no longer used. So let's see how we can work with references. Let's modify the function to accept a reference to a string, and a reference is indicated by an ampersand. So in this case, s will be a reference to a string, and it will just return a usize. And we'll see that if we pass s as reference, so s1 as reference, s1 will still be accessible. So now for debugging, we can say that we print first s1 and then its length. So let's see if this compiles. Okay, this is good. So s1 hello, s length, oh, this is a incorrect spell, but whatever. So hello has length 5, and this is what we want. So in this case, the compute length function just reads the data, so it just reads the string and it does not alter it. So this is an immutable reference. We can also have mutable references in Rust, and this is useful when we want to mutate the data we are working on. So for example, we can define a change function which just appends some text to the string that we pass in. So for example, let's define the function change, and this will still accept a reference to a string, and it will return a reference to a string. So here I have the string, and we do just like that. So s, and then push string. Okay, guys. So here we can call the change function on S1. And this will not compile. Oh, this actually does not return anything. So we can leave it empty. And this will not compile because this is an immutable reference. So if we run this, okay, what it says here is that it cannot borrow S, or rather the data inside of S, as mutable, because it's behind an ampersand reference, which is just an immutable reference. So we can make the reference mutable by prefixing it with a mute keyword. So we can write mutable references as ampersand and then mute, which of course is mutable, and then the type. And so here we do the same. So this actually does not return anything. Ah, sorry guys, I got it wrong. Here the reference stays the same, but we have to tell the compiler that S1 is gonna be a mutable variable. Okay, this is okay. Okay, it was correct. So if we run this, and let's just print the result. So S1 after calling change, and now it should be okay. Okay, so here, before calling change, S1 is hello and has length 5, and then S1 after calling change is hello world. Okay. And so, to recap, just as variables are immutable by default, so are references. If we want to enforce the mutability on references, because we want to alter the data they are pointing it to, we have to mark them as mutable, just as variables. So in the same scope, you can either have one mutable reference, so just one possible reference that is gonna write on the data, or you can have multiple immutable references, because immutable references are just readers, so they're not gonna do a data race. So for example, here we can forget about the change function. And instead we can just define a mutable reference to S1. And this compiles just fine. But if we add another mutable references, the script will not compile. Okay, now it's compiling because we are not using these variables, so their scope ends just after their definition. But if we do something like this, okay, this will be an error. So here it says, first mutable borrow occurs here, and then second mutable borrow occurs here. And the error is that we cannot borrow S1 as mutable more than once at a time. Of course, within the same scope. So for example, if we print S2 here, so the end of the scope is here. Now we do the same thing with S3. Okay, I don't know why it says that that's an error. Okay. But now it should be fine. Yes. So here basically, guys, we just consume S2 after its definition in the println macro. So here is the end of the scope. And then we consume S3. We define and consume S3. And this is okay. So guys, just to recap, here are the reference rules. So references cannot change data they point to, if we are talking about immutable references, but just as variables are immutable, we can make them mutable and we can make mutable references. But in the same scope, you can either have one mutable reference, which is one possible writer, or multiple immutable references, so multiple readers. And this is good for remember the rule, because of course we can have multiple readers because they are not gonna alter the data, so they can access the data at the same time, but they cannot write simultaneously to the same memory location because this is gonna create bugs at runtime. Okay guys, so this is it for ownership and references, and thanks for watching, and see you on the next video. Bye!